All right, folks, I'm ready to get started. Welcome back, everyone. Welcome back to the first class of the final 3 weeks of the semester. So we're finally there. We're finally at the very end. There's a lot to be done on your end. So I don't necessarily envy you, but I do, as always, try to encourage you to stay focused and don't let the volume of work overwhelm you. Just kind of take it one day at a time, one assignment at a time. Lay out a plan for yourselves. Don't kind of just let it all hit you at once at the end and then figure it out. Like, you want to just always kind of have foresight and know what's coming so that you can take care of things in the right way. I do have a lot of work to do as well now, but definitely once your finals are done, I'll have a lot of work to do. So, and with the papers, got to grade the papers. But for now, I'm good. Nonetheless, there are still a good amount of chapters to cover. We have this chapter, and then actually just two more after this. So we're going to finish chapter 10 this week. It's a fairly long chapter, so it takes about 4 class sessions to cover it. So we'll continue it today, finish it on Thursday. I'll open up a mini paper for it, which will be due the following Thursday. And then that'll pretty much dry up all options for mini papers. The mini paper for the open chapter paper is due on the 30th, so that's this weekend. And then the actual paper is due a week from Tuesday, so I don't want you writing mini papers that final weekend. I want you polishing up your final paper and turning it in. So I don't really want to assign one for chapter 11 because then it's just you're just not really doing anything at that point. You're just rushing to get things done and you're not thinking about things. So I've for those people that have not done enough at this point, like, you've had a lot of opportunities the entire semester to write these papers, and at this point you should be at the stage of either having already completed the final paper or on the verge of doing so. And I do suggest to those of you that have not done so but have completed the mini papers to go ahead and do that. Finish the paper as I suggested last week as well. Ideally, some of you took the weekend to do that, knocked it out, but if you didn't, knock it out this week. Get it done. Put your 3 papers together. Write an introduction. I'm the firm manager. This is what's going on in my firm. These are the 3 observations I made. Brief summary. Done. Introduction. Put the 3 papers together. Some subtitles for each one, just signifying that there's different sections, and maybe, like, write a little something at the end of each section. Just kind of flow from one section to the next. Write the introduction to kind of write the conclusion and mirror the introduction, and then you're done. So it's not a hard process at the end if you've already thought about the papers. Plus, you could take a moment to maybe think about your mini papers a little bit more, make sure that you polish off the logic so that it's sound and all your points are made clearly. But beyond that, if you've done it, it shouldn't be too much of a hassle for you to get it done. Have it set, ready to go. You could already submit it digitally, I think. Did I already open up the digital submission for final paper? No. Okay, I'll set it up this week. And of course, the hard copy I need to be submitted to me by the day it's due, which is a week from today. No, 2 weeks from today. 2 weeks from today. So again, like I mentioned, you can turn that into me either in class, during my office hours, or anytime before it's due. You can slide it under my door. I'll send an email at some point soon just specifying that you should, on the cover page, list that you are in my 308 class that meets Tuesdays and Thursdays, because I have another 308 class and I need to make sure that I can keep them separate so I know whose paper is whose. But beyond that, it should be really easy for you to turn it in and get that out of the way and it not be a burden for you. So that's ultimately the goal here. That was the goal of the entire system. Generally, people give me positive feedback on that, like the fact that, like, I set it up that way, because by the end, when other stuff is due, they've already gotten the paper out of the way, essentially, which is not the case for other classes. Alrighty, are there any questions about anything you'd like me to address before we move on to the material for today? Great. All right. So we're working on game theory. So we've been again talking about how game theory is sort of this method of analyzing situations where decision making is not just based on one's own conditions, but it's also based on the decisions that are made by those also involved in the situation. In this case, in the case we're talking about in this class, obviously it's oligopoly. So a few firms that have large market shares in a market that basically dominate the market, define the market. But when they do that, they have this situation where they are trying to figure out how to maximize their profits, but they also have to be thinking about what their rivals are doing, and so it becomes complicated. We had Chapter 9 cover a few scenarios that deal with possible situations that firms can get into and how those can be approached given the analysis. And then in this chapter, we have a similar sort of situation, but a different approach. We use this approach called game theory, where again, you kind of set up this situation where decision making is interdependent as a sort of game, where the decision makers are the players and the choices they can make are their strategies, and the options they choose will lead to payoffs, and those payoffs will dictate optimal choices based on the fact that there is that interdependence. So we went through the first sort of round of these type of approaches to analyzing the oligopoly situation, which is the one-shot sequential games, where the decisions are made at the same time and the interaction happens one time. And we talked about how the oligopolists wind up in a prisoner's dilemma, essentially, where their best option is just to charge the lowest price possible, the lowest price being marginal cost ultimately, and that leading them to have zero economic profit. That is the Nash equilibrium for the game, because again, like there's no way for them to make a kind of arrangement in order to make better profits, to work with their rivals and take advantage of the market in the way a monopolist would. So that's the one-shot situation. That's when the games are played once. So we talked about how the gas station attendants, if there's two gas stations on the same block and they both kind of wake up in the morning and call their manager and say, hey, we should put this price, then that kind of mirrors that situation. Another situation that mirrors that is like when firms are introducing products at the same time. So if you think about the video game manufacturers, and generally during Christmas, that's when they'll introduce their new consoles, and they'll introduce them at the same time, and they don't know what their rivals are going to price. So that's kind of like a one-shot type of situation versus repeated plays of these games where these firms are competing with each other on a regular basis, month after month, year after year. And that changes, as we'll see, the outcome of the game. The Nash equilibrium won't necessarily be for the firms to not collude, not work together, and not earn zero economic profits, but to actually be able to reap benefits from the market that not necessarily ultimately do get them to that monopoly level collectively, but closer, and definitely a better outcome than what you would find in the one-shot play of these games. And it's going to depend on a couple of things, and we'll talk about the intricacies of that as we move forward. So the first case that we'll consider is the infinitely repeated game, a game that has no end. So the players are just continuously interacting, competing in whatever dimension it is that they compete on. Obviously, it's pricing for the firms that we're talking about here. And when that is the case, and they have to consider the benefits of cheating on agreements versus the cost of cheating on agreements. And when they're thinking about the cost, they're thinking about the revenues that they could gain indefinitely into the future, which means that they then need to consider the present value of those profits into the future. And so therefore, ultimately, the incentive to either cheat or not on these collusive agreements will be based a lot on the interest rate that's being set in markets, because again, that is what dictates the discount factor, which is what dictates the present value of profits. So we'll look at how that works. And then we'll talk about finitely repeated games, games where the firms are interacting continuously, but there is an end to that. Like maybe they know that the products that they're selling to each other are going to become obsolete maybe at some point, and therefore their competition will end. Now, whether or not they know when exactly that end happens will also change the outcome. So we'll talk about those two cases as well. Either they know the end or they're uncertain about exactly when it'll end, even though they know that it's coming. All right, so just briefly going over the stuff we already covered. Again, we're talking about either games where people move at the same time or sequential move games. So we'll talk about sequential move games on Thursday via what's called the extensive form of the game, which is like a game tree, versus what we've been looking at, which is the normal form of the game, which is just a table that we've been looking at. And again, the games can be played either once or they can be repeated, and that is what will change the outcome. So again, last week we looked at simultaneous move one-shot games. And again, it looks like this. So again, the players have their strategies either on the rows or the columns, and the outcomes depend on what both players choose. So if player B chooses left and player A chooses down, then player A gets -10 and player B gets 7. So that's what the two numbers in the boxes again represent. The number on the right, on the left represents player A's payoff, and the number on the right represents player B's payoff. So we talked about dominant strategies, and that sort of being one of the ways to sort of maneuver this sort of complex type of interaction, where if one can identify a dominant strategy, then they should play that dominant strategy. And essentially, identifying it again means that you take the perspective of a player and consider so taking the perspective of player A, we're going to consider what would player A do in response to player B doing each of their moves, either left or right. Well, if player B chose left, I could either go up or down. Obviously, up is better than down. And if player B chooses right, then I can go up or down. And obviously, in this case, 15 is better than 10. And so I would choose up again. And therefore, regardless of what player B does, either left or right, I'm going to choose up, because it always benefits me more to choose up. And therefore, I have a dominant strategy to play up. And therefore, in this type of situation, I will always play up, no matter what, regardless of what goes on, as long as the payoffs remain the same. We also talked about the fact that if somebody does not have a dominant strategy, that they might play what's called a secure strategy. And that's generally for players in these situations that are very risk averse. They don't like loss at all. They don't like complete loss at all. They're afraid of to take any type of risk. And if they don't take other information into consideration beyond just like the worst possible outcomes for themselves, then the secure strategy, also known as the maximum strategy, is one that guarantees the highest payoff given the worst possible scenario. So they look at the worst possible outcomes, and then they choose the outcome that is best out of the two worst outcomes for them. So again, let's say if we're taking the perspective of player B, and if player A chooses up, then player B can either choose left or right. Right would get him the worst possible outcome. If player A chose down, then player B can either choose left or right. And in this case, left would get him the worst outcome. They'd get 7 instead of 10. And so 8 is better than 7. So that gets them the best of the worst outcomes. So therefore, the secure strategy for player B would be to play right. And that's how you can identify a secure strategy. All right. I'm going fast because this is all review. Also mentioned the Nash equilibrium last week. Nash equilibrium being the set of strategies that no player has any incentive to deviate from. Games may or may not have Nash equilibria. Games may have multiple Nash equilibria. If both players have a dominant strategy, and where those dominant strategies overlap will be a Nash equilibrium, but you don't need a dominant strategy to have a Nash equilibrium in the game. And basically, to identify it, you go through each player, figure out what they would choose optimally in response to each of their opponent's moves, and then do the same thing for the other player, and then the boxes that overlap in those optimal choices will be Nash equilibria. And again, I mentioned about how the Nash equilibrium is very powerful because it allows us to provide some certainty and be able to make real world predictions in these type of situations where it's very uncertain what's going to happen, because again, you can't just optimize your behavior based on what you do. You have to take into consideration what your rival's doing, and that creates a lot of uncertainty, because ultimately, even though you might know what their strategies are and what the payoffs are, you don't actually know what they're going to do. But you can get some certainty out of it by identifying a dominant strategy or a Nash equilibrium or a couple of Nash equilibria, which we looked at last time on several applications. We looked at how games can have multiple Nash equilibria. Anyway, I'm not going to go through this because we'll have other examples today to identify it. Should have taken out these. All right, there we go. All right, now let us move on to infinitely repeated games. All right, so based on prior analysis of one-shot pricing games, again, where the firms interact one time, and also we looked at advertising games, where the firms have to decide whether to advertise or not, one might be led to believe that collusion is impossible in an industry, again, because we identified the fact that the Nash equilibria in those games is for the firms not to work together, and basically for them to have the worst outcome, a worse outcome than they would have if they did work together. So this conclusion is not correct, though, the fact that it's impossible for them to work together, since firms in some industries do not play a one-shot game, but instead compete repeatedly week after week, year after year. The appropriate mode of analysis is to consider a situation where the game is played repeatedly over time. So we'll, again, in this part of the chapter, look at the infinitely repeated games, games that are played over and over again forever. So during each round of the game, players receive payoffs due to the time value of money. The fact that, again, $1 today is worth more than $1 tomorrow, because $1 today can be invested and you can get a return on that dollar. And so therefore, if you don't do that and you just let the dollar kind of sit idle in a year, you're losing that opportunity cost, that implicit cost to holding $1. And therefore, $1 in the future is worth less than $1 today. So players must appropriately discount future payoffs when they make current decisions. All right, just quick review of present value. The value of a firm is the present value of all future profits earned by the firm. Stock prices are essentially a present discounted value of future dividends that a stock would pay out, which is, of course, profits. I is the interest rate. Pi I represents profits in the year I, where I equals 0 to t years. The value of a firm will be in the value of a firm that will be in business for t years is, so we assume the period of time that the firm will be in business is t years, kind of leaving it open-ended to sort of establish the infinite nature of the situation. All right, so the present value of the firm would be the profits that they earn today plus the profits that they earn a year from now discounted to the present. So 1 over 1 plus the interest rate raised to the first power to represent the 1 year period. Plus profits obviously earned in 2 years from now, discounted to the present by 1 over 1 plus I squared. And then, of course, the third year, all the way to the tth year. And then, of course, we can represent this sum via sigma notation, where, again, this symbol represents sum, and the bottom represents the time the period starts, and then the top represents when it ends. And so this is the term that would be added for each of these periods from 0 to t, which is what you see here. Over here, we have the same term, but we have 1 plus I raised to the 0 power. Anything raised to the 0 power is equal to 1, so you have just like pi in that first period. All right, so if the profits earned by the firm are the same in each period, so let's say that these profits do not change, so it's like just a standard maybe dividend that doesn't depend on actual revenues, just like it's something that's pre-established as being constant. And let's say the time horizon is infinite, then this formula simplifies to pi times 1 plus I over I. So this sum, if these are the same, if the profits are the same and the time period is infinite, the sum of these will add up to this term here. That's the sum of a geometric series. It's a basic mathematical property. It's easy to derive. It's something you would learn in Calculus 2 if you took Calculus 2. But if you haven't, just take my word for it. This is what this will add up to if it's to be added infinitely. All right, so this formula is very useful in analyzing decisions in infinitely repeated games because, again, one can weigh the benefits of cheating on an agreement, which is the excess profits you can gain from cheating, versus the cost of the agreement, of cheating on the agreement, which is the lost profits that you would gain from just colluding and, again, dividing up the market as a monopolist would. All right, so the way that firms can establish collusion over time is via what's called trigger strategies. And I'll talk about what that means in a second. So consider this simultaneous move Bertrand pricing game. So remember, the Bertrand pricing game is a situation where oligopolists are competing based on pricing. And we saw that in the examples from last week and also in the end of the last chapter that the outcome of a Bertrand pricing game is for the firms to charge their marginal costs because they wind up in a price war, and for them to make zero economic profits, unless they can collude together, work together. So here we again have a situation where they can each charge a low price or a high price. They could, again, work together and say, hey, let's rig the market, let's charge a higher price and lower the amount of output so that we can make higher profits. But there is incentive for them to cheat on that agreement. If firm A abides by the agreement, but firm B chooses to charge a low price, then firm B gets all the profit because everybody buys from them, and then firm A winds up losing because nobody buys from them, and their profits get a significant hit. Both of them have the incentive to cheat. Again, firm A could be the one that's cheating, charge a low price, where firm B charges a high price. And so because both have an incentive to cheat, they both would wind up cheating, and both would wind up charging a low price, therefore earning zero economic profit. So that's how it could go in a one-shot situation. As we know, therefore, this is the Nash equilibrium for the one-shot play of this game. Suppose now that the firms play the game in the table day after day, week after week, for all eternity. So it becomes possible for them to collude without fear of being cheated on. They do this by using what's called, again, trigger strategy. So a trigger strategy is a strategy that is contingent on the past plays of players in a game. It's also known as tit for tat, for those of you that might have learned it that way. I do teach it that way in my introductory econ class, as well as my 310 class. So a trigger strategy, again, is a strategy that is contingent on past plays of players in a game. So players will first start playing what they think is best to play, and then they will continue playing that as long as their rival plays the same thing. But if their rival changes their behavior, then they will change their behavior, and then everyone will start playing that other strategy from that point forward. So a player who adopts a trigger strategy continues to choose the same action until some other player takes an action that triggers a different action by the first player. All right, so to see how this works, suppose that firm A and firm B secretly meet, they break the law, they don't care, and they agree to collude, and they raise prices. So they get together and they're like, yes, let's rig the market, let's take the profits and just limit the amount of output, cause inefficiency, but hey, that's what they want to do. If firm A cheats, right, because again, we know firm A has an incentive to cheat, and pulls, then it pulls the trigger that leads B to charge the low price forever after, and vice versa. So firm A cheats, even though firm B doesn't cheat. So that's this option here, where again firm B abides by the agreement, firm A does not. Firm A gets the high profits, firm B winds up losing. But from that point forward, firm B is going to just charge a low price because that's what firm A did. They're going to basically just play tit for tat, do exactly what their opponent did, because again, firm A triggered it. This is the trigger strategy result. So if both firms adopt this trigger strategy, there are conditions under which neither firm has an incentive to cheat on a collusive agreement. So let's say if the present value of the cost of cheating is greater than the one-time benefit of cheating, then it does not pay for a firm to cheat and high prices can be sustained. So again, if the profits that are foregone by cheating today in the future are greater than the amount you get from cheating today, then obviously it doesn't make sense to cheat today because you can benefit more in the future. Foresight, folks. Having foresight is important. So suppose the firms agree to the collusive plan just outlined and that firm A believes that firm B will live up to the agreement. If firm A cheats by charging a low price, its profits will be, of course, $50, right? Again, firm A cheats, they get the $50, firm B gets the negative 40. But after that, every round after that, they will receive 0 in profits. So the best choice for firm A when firm B charges the low price in these future periods is to charge the low price to earn 0. As I mentioned, that would be the result in every subsequent round. So if firm A cheats today, the present value of his profits are obviously just $50 because they would get 0 in every period thereafter. If firm A does not cheat, it will earn $10 every period forever. So the present value of firm A's profits, if it cooperates, meaning it does not cheat, is going to be, again, pi times 1 plus I over I. So $10 times 1 plus I over I, where I is the interest rate. So whether or not this will be worth it to them to cheat will depend on the interest rate. So for the numbers in this example, there's no incentive to cheat if, let's say, again, the $50 is less than the present value of the income stream into the infinite future. So you can solve for that interest rate. What would that interest rate need to be in order for this to be less than or equal to this? And there would be no incentive to cheat. So again, you can just do algebra here. So multiply both sides by I, and then you want to combine your terms. So 10 plus 10i there. And then you want to combine 50i plus 10i, subtracting 10i from both sides, divide both sides by 40. That means if the interest rate is less than or equal to 25%, then there's no incentive for this firm to cheat. So if the interest rate is less than 25%, firm A will lose more in present value by cheating than it will gain. And therefore, it will not be in firm A's best interest to cheat in this case. And that's likely going to lead to them colluding because you're not generally going to find 25% interest rates in markets. Generally, it's very rare unless a country or a firm is like in really bad like credit standing, and essentially they need to provide a higher interest rate to lure people in to be able to even sell their bonds or their assets. But even in those cases, people would have to be really risk loving, like they would really be willing to take risk, because those kind of things, if you have any kind of instrument paying you that kind of interest rate, that means that it's very likely that's going to default. So you probably wouldn't want to buy that instrument. Anyway, since firm B's incentive are symmetric, meaning firm B has the exact same situation, has to consider the exact same benefits and costs to cheating, the same will be true for firm B. As long as the interest rate is less than or equal to 25%, then firm B will not have an incentive to cheat. Thus, when oligopolistic firms compete repeatedly over time, it's possible for them to collude and charge high prices to earn $10 each period. This benefits firms at the expense of consumers, obviously, because we would all benefit from this, charging low prices, and also increasing the amount that's transacted, the amount that's supplied in the market. And it also leads to that deadweight loss, which explains why there are laws against collusion. So that's why there are laws against them doing this, because again, it is ultimately hurting markets, even though it helps the firms. It hurts society because there is that deadweight loss, that loss of mutually beneficial transactions that could occur that would result in higher consumer and producer surplus, which means that there's more benefit from the markets for everybody. The markets are more efficient. All right, so that gets us just to the summarizing principle: sustaining cooperative outcomes with trigger strategy. Suppose a one-shot game is infinitely repeated and the interest rate is I. Further, suppose that the cooperative one-shot payoff to a player is this profit. So that would be, in the last example, it was $10. The maximum one-shot payoff if the player cheats on the collusive agreement is pi cheat, so that would be the $50 profit. And the one-shot Nash equilibrium payoff is pi n, which was the zero amount that we saw. Then you have this situation here. This condition has an intuitive interpretation when rewritten as this expression here. So if we write this expression as this expression, what this tells us is that the left-hand side represents the one-time gain of breaking the collusive agreement today, which again is the difference between the profits you gain from cheating minus the profits you gain from cooperating. And the right-hand side represents the present value of what is given up in the future by cheating today, which is again the difference between your cooperative profits and the Nash equilibrium profits, discounted to the present by the interest rate. So again, if this is less than this, then the outcome can be sustained in the infinitely repeated game with the following trigger strategy. Cooperate if no player has cheated in the past. If any player cheats, punish the player by choosing the one-shot Nash equilibrium strategy forever thereafter. So that's just a way of thinking about why it is possible for these firms to collude, work together. But again, it is illegal for them to do that. So it is risky for them to even take that risk to do it. So we'll talk about how that sort of gets resolved in a bit. Let's do a demonstration problem first, though. Suppose firm A and firm B repeatedly face the situation presented in the table, and the interest rate is 40%, let's say. The firms agree to charge a high price in each period, provided neither firm has repeated this agreement in the past. So there's a trigger strategy they're all willing to engage in. What are firm A's profits if it cheats on the collusive agreement? What are firm A's profits if it does not cheat on the collusive agreement? Does an equilibrium result when the firms charge the high price each period? All right, so let's look at each question in turn. What are firms A's profits if it cheats on the collusive agreement? Right, exactly. If firm A were to cheat, they would charge a low price. Firm B would charge a low price, and therefore firm A would get the 50. If firm B lives up to the collusive agreement, if firm A cheats, firm A will receive the 50 and 0 forever after. All right, what are firm A's profits if it does not cheat on the collusive agreement? Well, we look at the present discounted value of that. If firm B lives up to the collusive agreement and firm A does not cheat, the present value of firm A's profits is equal to pi times 1 plus I over I, which equals 10 times 1 plus 0.4 over 0.4. So if I were to give you a question like this, I would give you this so that you wouldn't have to know that. I would give that to you. I don't like randomly making you memorize equations, but you should understand how to derive equations. So all the stuff we did in the last chapter with the reaction functions and all that, like that's stuff that you can do by just taking information from the problem and getting to your solution. Take some complicated steps, but if you understand the process and the logic, it's not difficult to get to it. But this obviously you can't derive that, so I would give you something like that. So 10 would be the profits because they would each charge the high price each period and get $10 in profits each. Yeah, it's the interest rate that we assumed was going in the market. All right, so the present value therefore is going to equal, in this case, $35. All right, does an equilibrium result where the firms charge high prices each period, therefore? No? Okay, why not? So think about what that means to be in equilibrium where they charge a high price each period. That means they're colluding every period, right? So right. So therefore, it makes they have an incentive to do what now? Just to cheat, right? Cheat, get the $50. $50 is better than the present discounted value of $35 infinitely, given there's a 40% interest rate. So, given that there's a 40% interest rate, profits indefinitely will not uh, equate or even surpass the $50 profits of cheating today. So, therefore, in this case, since the payoff matrix is symmetric, each player has an incentive to cheat on the collusive agreement, even if it believes the other firm will not cheat, and therefore they will earn zero economic profits. In each equilibrium, each firm will charge a low price and earn zero profits each period. All right, so let's talk about factors affecting collusion in pricing games. So the sort of realistic context that will affect that outcome that we just talked about from actually happening. So one thing that they need to consider is who their rivals are, so that they know whom to punish should the need arise. So they obviously the world is not made up of just two firm duopolies. Most oligopolies are made up of roughly 2 to 10 firms. So they need to know who it is that they're competing against, and so that they can punish them. They need to know who their rivals' customers are, so that if punishment is necessary, they can take away the customers by charging low prices. They need to know when their rivals deviate from the collusive agreement, so they know when to begin the punishments. And they must be able to successfully punish rivals for deviating from the collusive agreement. So there has to be a credible threat to cheating. Like you can't just threaten and then not have anything to back it up. You know, like when we say that we're sending an armada somewhere, but we're really just sending it in the opposite direction. All right, number of firms. So let's consider each of these in turn. So the number of firms. The fewer the firms, the easier it is to collude, obviously. When there's less players in the game, there's less chance that people are going to deviate from their optimal behavior. So if there are n firms in the industry, the total amount of monitoring that a firm has to do in order to sustain the collusive agreement is going to be n times n minus 1. So each firm is going to have to monitor all their other rivals minus themselves. The total number of monitors needed in the market grows rapidly as the number of firms increases. If there are 5 firms, each firm must monitor 4 other firms, so the total number of monitors needed in the market is 20. The cost of monitoring rivals reduces the gains to colluding. So again, you can benefit from colluding, but if it costs you a lot of money to keep track of what all your rivals are doing, then that obviously will affect the benefit of colluding. So under these circumstances, the threat used to sustain the collusive outcome is not credible, and the collusion fails if there's too much monitoring necessary and it hits the profits enough where, again, it kind of offsets the incentive to maintain the collusive agreement. How large the firms are will also affect whether or not this type of collusive outcome can be sustained. So economies of scale exist in monitoring. Again, economies of scale means that the larger you are, the lower your average cost. So monitoring and policing costs constitute a much greater share of total costs for smaller firms than larger firms. A large firm with, say, 20 outlets can monitor the prices charged by a small competitor with one outlet by simply checking the prices at that one store. To check the prices of its rival, the smaller firm must hire individuals to monitor 20 outlets, which obviously will be a bigger chunk of their profits because they're smaller. The history of the market, what's happened up until the current point. So one key issue not addressed as far as how firms reach the understanding to collude. One way is for the firms to explicitly meet and, again, verbally warn their rivals not to steal their customers or else they will be punished. Alternatively, firms might not meet at all, but instead gain an understanding over time the way the game is played and thus achieve what's called tacit collusion. So that's ultimately probably the best and most common way that these kind of agreements are established and sustained over time. It's more a matter of like the firms knowing that they should be behaving in that way versus them getting together and agreeing upon it. They kind of know that that's how they should be pricing given what their rivals are doing. And so it does allow them to sort of implicitly, tacitly, tacit means like, you know, just not necessarily talking, like in the shadows, sort of like just you know, coming to conclusions without that kind of explicit interaction. So tacit collusion occurs when the firms do not explicitly conspire to collude but accomplish collusion indirectly. In contrast, if a firm learns over time that its opponents are unable to successfully punish it for undercutting prices, then tacit collusion will be unlikely to result. If firms observe that rivals do carry out their threat, this history will result in collusion. So again, the experience in the market is very important to either establishing these arrangements or to maintaining them. And then, of course, the punishment mechanism needs to be credible. So the pricing mechanisms firms use also affect their ability to punish rivals that do not cooperate. In a posted price market where all prices are explicitly posted and there's a single price charged to all of a firm's customers, the cost of punishing an opponent is higher than in markets in which different customers are quoted different prices. A firm that wishes to punish a rival by stealing its customers not only has to charge a low price to the rival's customers, but also must lower its own price to its customers. In industries in which different prices are quoted to different customers, in which there's what's called price discrimination, which we'll talk about in the next chapter, a firm can punish its rival by charging the rival's customers a low price while continuing to charge its own customers a higher price. All right, let's do a couple of applications of the infinitely repeated games. This is for product quality. So the theory of infinitely repeated games can be used to analyze the desirability of firm policies such as warranties and guarantees. Consumers desire durable, high-quality products at a low price, obviously. Firms wish to maximize profits, so those are the opposing sort of interests there. In a one-shot game, any profits made by the firm must be made today without the prospect for repeated business. So if the firm's only selling a product once, they don't need to think about their reputation in markets, their reputation for quality, etc. So obviously warranties and guarantees aren't going to be necessary or important to a firm of that sort. So a firm may have an incentive to sell shoddy products, especially if consumers cannot determine the quality of the products prior to release. So that might, a case like that you can think about like in Amazon. Sometimes like you'll encounter just like random sellers that sell like this one very unique thing, but you have no idea like if it's going to be of quality or not. There's no ratings for the product. There's no sales history, and you just kind of take a shot in the dark. Sometimes it doesn't work out. I'm sure you've experienced this. I've experienced it. Sometimes it does. But again, like, you know, with firms that don't have that kind of pedigree where they, you know, have like this history of quality and they have a name to uphold, you know, they have less incentive to actually give you something of quality. In a one-shot play of the game, the Nash equilibrium strategy is for the firm to produce a low-quality product and for consumers not to buy the product. So we can demonstrate that via, again, a normal form of the game where the consumer can either buy or not buy, and the firm can either produce a low-quality product or a high-quality product. They produce a low-quality product, the consumer doesn't buy, nobody gets anything. They produce a low-quality product, the consumer does buy, the firm makes money, consumer loses more than they didn't buy. Firm makes a high quality product, consumer doesn't buy. Again, high quality means that they put in some money, so the firm loses, customer doesn't get anything. But if they make a high quality product and the consumer does buy it, obviously everybody wins there. But we can identify why the Nash equilibrium in a one-shot play of the game is for the consumer not to buy a product and for the firm to make a low quality product by just going through the paces of identifying a Nash equilibrium. So again, we assume the role of the consumer and consider what they would do in response to each of their rivals' actions optimally. So if the firm makes a low quality product, what should the consumer do? Not buy, right? Because 0 is better than negative 50. If the firm makes a high quality product, what should the consumer do? They should buy. Does the consumer have a dominant strategy? No dominant strategy. They're going to play a different strategy in response to each of their rivals' possible strategies. All right, taking the perspective of the firm in response to the consumer not buying, what should the firm do? Low quality product, right? 0 is better than negative 10. Remember, the payoffs on the right in each cell represent the payoffs to player 2, which is in this case represented as the firm. In response to the customer buying, what should the firm do? Low quality product. Does the firm have a dominant strategy? Yes, the firm does have a dominant strategy. They will produce a low quality product regardless of what the consumer does. They will play the same strategy regardless of what their rival does. They have a dominant strategy. Is there a Nash equilibrium here? What is the Nash equilibrium? Exactly. Consumer chooses don't buy, firm chooses low quality product. We know that because this is the set of strategies where both of their optimal choices overlap. So that's how you identify Nash equilibrium. Again, there could be multiple, there could be none, but you have to be able to figure out if there is one or not. All right. So in a one-shot, so again, if they only play this game once, the customer chooses not to buy the product because she knows the firm will take the money and run, and therefore that winds up being the outcome. The story differs if the game is infinitely repeated. If the consumer tells the firm, I'll buy your product and will continue to buy it if it's of good quality, but if it turns out to be shoddy, I'll tell all my friends never to purchase anything from you again. Essentially, a trigger strategy. In that case, they have an agreement where the consumer will buy if the firm will make the high quality product, but if the firm chooses to cheat on that agreement, then the customer will not buy forever after, including all other customers, because again, word of mouth will become prevalent. So given this strategy by the consumer, if the interest rate is not too high, the best alternative is to sell the high quality product. When the interest rate is low, the one-time gain will be more than offset by the lost future sales. So again, the interest rate will be the main determinant of what the outcome will be here, but generally you'll have low enough interest rates where it will not be worth it for the firm to cheat. The present discounted value of profits into the future will be worth them producing high quality products. So the lesson to be drawn from the example is twofold. First, if your firm desires to be infinitely lived, it does not pay to cheat customers if the one-time gain is more than offset by lost future sales. Aside from the ethical reasons why high-quality products should be produced, obviously, oftentimes firms don't consider ethical reasons to do things. It's all about profit and loss. So this justifies why they should continue to produce high-quality products in terms of like the numbers. All right, so this is true even if your firm cannot be sued or if there's no government regulation against selling shoddy merchandise, again, because your customers will not buy from you in the future. Second, you should recognize that any production process is likely to have bad runs. So even though your intentions are to produce high quality products, you never know. You might have a bad batch of inputs at some point that might result in some bad products being distributed. To guard against this, many firms offer guarantees that the product will be of high quality. If an error occurs in production, the consumer can obtain a new item, be satisfied, and not punish the firm by spreading the news that it sells shoddy merchandise. And that's why, given the nature of the situation that we can analyze with this this game strategy approach, we gain these same intuitions that we normally would about how firms should go about operating. But again, it's good to have these kind of tools and to be able to analyze situations with them, because then it provides a sort of formal basis for why firms should operate in these ways versus just giving them sort of just trying to give them the benefit of the doubt that they'll do the ethical thing. All right. So let's look at finitely repeated games now. So again, the games could be played indefinitely, but in reality, that's not always the case. And sometimes the games will end. There will be a time period where maybe the products will become obsolete. Things of that sort could end the repeated game, and that will change the outcome of the game and how the firm should go about uh, uh, managing the firm within the game. So we'll consider two classes of finitely repeated games: games in which players do not know when the game will end, and games in which players know when the game will end. So let's consider the games with an uncertain final period first. I think we'll finish with just this section today, with the uncertain final period. So suppose that there's two duopolists and they're repeatedly playing this pricing game until their products become obsolete, at which point the game ends. So it's the same game we've been talking about, the Bertrand pricing game, with the same Nash equilibrium, with the same type of profits that you would gain if the firms colluded. Suppose the firms do not know the exact date at which their products will become obsolete. So they don't know when the game will end. So in this case, we're gonna incorporate some probability into it. So we'll let the probability the game will end after a given play be equal to theta. So theta is just a 0 with the line in the middle. It's a Greek letter. It's just a placeholder for the probability here. Probabilities in general can be between 0 and 1. If you're thinking about a situation, all possible outcomes, their probabilities need to sum to 1, right? Something is going to happen, even if that thing that happens is nothing. Nothing will have a probability as well. It might be 0, it might have a higher probability than that. All right, so when a firm makes today's pricing decision, there's a chance the game is going to be played again tomorrow, and there's a chance that it will not. If the game is played again tomorrow, there's a chance that it will be played again the next day, and so on. So again, theta is going to represent the probability the game will end tomorrow. So let's say theta is equal to 1/2. That means there's a 50-50 chance the game will end tomorrow. So with this kind of uncertainty, maybe you can think about like the government is doing an analysis of the product that's being sold, and they're likely to maybe outlaw it at some point, but you don't know when. That could be like a situation that would apply here. So let's say there's half a probability the government will make the determination and outlaw the product, by next week or whatever, bath salts or something. I don't know. All right, so there's a half. So there's a 50% chance that the game will end tomorrow, and there's a 50% chance the game will end the day after that. So there's a 50% chance times a 50% chance the game will end the day after tomorrow. So to get that probability that the game will end after the second play, you multiply the probability of it ending on each day. So again, 1/2 times 1/2 equals 1/4. So there's a 1/4 probability the game will end after a second play. More generally, there is a 1/2 raised to the tth power chance that the game will end after t plays of the game. So if the game will end 3 days from now, then it's 1/2 raised to the third power. 4 days from now, 1/2 raised to the fourth power, and so on and so forth. All right, when there is uncertainty regarding precisely when the game will end, this infinitely repeated game exactly mirrors the analysis of the infinitely repeated game. So you're going to get the same outcome as you would get with the infinitely repeated game if if there is now no clear sign that the game will end, if there's complete uncertainty when the game will end. So if the firms adopt a trigger strategy, as we mentioned in the last section, and a firm deviates by charging a low price, the other firm will punish it by charging a low price until the game ends. So it's exactly the same situation. And again, the firms don't need to explicitly get together. They can tacitly collude. For simplicity, assume the interest rate is 0 so that the firms do not discount future profits. So we're not going to think about the interest rate right now because we're going to be thinking about probability. So we'll just think of the interest rate as being equal to 0, and we'll look at how the probability will affect the outcome. The probability the game will end the next day. So given such trigger strategies, the question is whether or not firm A has an incentive to cheat by charging a low price. So if A cheats by charging a low price when B charges a high price, A's profits, again, will be 50 today, but 0 in all remaining periods of the game. If firm A cheats today, it earns, again, those $50 regardless of when the game ends. If firm A does not cheat, it earns $10 today. In addition, there's a 1 minus theta probability the game will be played again because there's a theta probability the game will not end. So therefore, 1 minus theta gives us the probability the game will continue. So there is a 1 minus theta probability that the firm will earn $10 tomorrow. There's also a probability of 1 minus theta times 1 minus theta, or 1 minus theta squared, that the game will not terminate after 2 plays, in which case A will earn another $10. So that's the probability that they will still be in business in 2 days and be able to earn that $10 from collusion on that second round. So carrying out this reasoning for all possible dates at which the game terminates, we see that if firm A cooperates, it can expect to earn $10 today times 1 minus theta times 10 tomorrow. We're not thinking about the interest rate right now, so again, we're assuming that the interest rate is 0, so we don't have that complication, just to understand how the probability plays into it. And then there's a 1 minus theta squared probability that they will be able to play a third round and earn that $10. Same thing with this round here, all the way to the infinite horizon, which means that we can again look at this as an infinite series, and we can see that the present value of the not the present value, well, it is the present value, but like the sum of this geometric series is going to equal 10 over theta. So like the actual profits that the firm will earn into the future is going to be equal to 10 over theta, given that, again, there is a probability that the game will end, and we have to continuously take that into consideration in each round of the game. So again, this is a mathematical result, something you would learn if you took Calculus 2. But take my word for it, it works. So 10 over theta. So so when theta is equal to 1, and therefore there's a 100% probability the game will end tomorrow, then the present value of cooperating is only $10, right? It's $10 divided by the probability, which is equal to 1. If theta is less than 1, the probability the game will end after 1 play is less than 1. There's a chance they will play the game again, and the profits of cooperating are greater than $10. So if, let's say, the interest rate is 25%, then you've got 10 divided by 25%, which is $40. So that would be the value of the profits into the infinite future, indefinite future, given that, again, that there's a probability that the game will end of a quarter in every single period. So the important thing to notice is that when the game is infinitely is repeated a finite but uncertain number of times, the benefit of cooperating look exactly like the benefits of cooperating in an infinitely repeated game, where you would, again, get the present value of the profits to be 10 times 1 plus I over I. So in an infinitely repeated game with an uncertain endpoint, 1 minus theta plays the role of the discount factor, 1 over 1 plus I, right? So when we did the summation of all possible payoffs, if you just look, if you went back to our old case and didn't think about probabilities but discounted each payment to the future, then you would have 10 divided by 1 over 1 plus I. So in this case, 1 minus theta plays that same role as the discount factor, 1 over 1 plus I. So players discount the future not because of the interest rate, but because they are not certain future plays will occur. So because they are uncertain that they will actually get to reap those profits, and those profits are worth less to them than they are worth closer to the present. Because, again, going further and further into the future, there's more and more uncertainty about whether even they'll be able to make those profits. And so, again, psychologically, they have to discount those profits because they don't even know if they'll get them. So they're worth less than like profits today that are certain, profits tomorrow that are more likely than profits 10 days from now. In an infinitely repeated game with an unknown end period, firm A has no incentive to cheat if it expects to earn less from cheating than from not cheating. For the numbers in our example, firm A has no incentive to cheat if the product, if the profits of cheating are less than or equal to 10 over theta, which is the profits from cooperating. And in this case, it's true if theta is less than or equal to 1/5. So if the probability of the game ending is less than or equal to 1/5 or 20%, then there's no incentive for the firm to cheat, and the firms can maintain a collusive outcome, whether it be tacit or explicit. If after each play of the game, the probability the game will end is less than 20%, firm A will lose more by cheating than it will gain. All right, since firm B's incentives are symmetric, the same is true for firm B. Thus, when oligopolistic firms compete a finite but uncertain number of times, it's possible for them to collude and charge high prices. The key is that there must be a sufficiently high probability the game will be played in subsequent periods. In the extreme case where theta equals 1, and therefore the players know that the game will end tomorrow, players are basically faced with the one-shot version of the game. The profits of cheating are $50, much greater than the profits of cooperating, and collusion cannot work. Each player will take advantage of the incentive to cheat, will cheat, and we will wind up in the Nash equilibrium of the one-shot game. When theta equals 1, the game is really a one-shot game. The dominant strategy for each firm is to charge the low price. All right, let's do a demonstration problem, and then we'll call it a day. Two cigarette manufacturers repeatedly play the following simultaneous move billboard advertising game with the featured payoff matrix. Again, when we're talking about advertising, the firms are also in a prisoner's dilemma. Because again, the advertising tends to have the only kind of effect it has is to have consumers switch brands versus bringing new consumers in. So the firms could agree to not advertise and therefore not cannibalize each other's customers from each other and save the money that they would save on advertising, and therefore they would each wind up here. Or one of them can say, I won't advertise, but then choose to advertise even though the other one abides by the agreement. The one that advertises then winds up getting high profits because they steal customers from their rival, and then the other firm winds up losing because they obviously lose customers. Both firms have incentives because the game is symmetric, and therefore they would both wind up not advertising in a one-shot version of the game, winding up in that Nash equilibrium that is worse than this equilibrium had they worked together. If there's a 10% chance that the government will ban cigarette sales in any given year, can the firms collude by agreeing not to advertise? So suppose the players have adopted a trigger strategy, whereby each agrees not to advertise, provided the other firm has not advertised in any previous period. If a firm deviates by advertising, the other firm will punish the offender by advertising until the game ends. If firm A cheats on the agreement, its profits are going to be $20 today, but $0 in all subsequent periods until the game terminates. If firm A does not cheat, it can expect to earn, obviously, those $10 today plus 1 minus theta, the probability that the game will continue tomorrow and earn $10, plus 1 minus theta times 1 minus theta, the probability the game will continue for 2 more days, times those $10, etc., into the future, which sums to 10 divided by theta, which is, again, 10 divided by the probability the game will end tomorrow, which is 10%. So therefore, the present value of the profits of the firm are $100 if the probability the game will end is low, 10% in this case. And again, we're assuming that there's a 0% interest rate, so we're not discounting these payments to the present via the interest rate. All right, since $20 is less than $100, $20 again being the cheating incentive, the firm does not have an incentive to cheat. The incentives for firm B are symmetric, thus the firms can collude by using this type of trigger strategy. All right, let's just call it a day. We'll continue this on Thursday. Have a good couple of days.